Thank you for inviting me to give this seminar in Cosmic Origins series of colloquia. So I will talk about the carbon cycle across galactic environments, which is a topic that I've been working on the last few years. And I will show you results from 3D models. To start with, let's go through the outline of the talk. I will give an introduction on PDRs and the ISM environmental parameters and what I mean. Do I mean by saying ISM environmental parameters? I actually mean three different things. The first is the FUV intensity, which is the intensity of the photons emitted by stars. The second one is the cosmic ionization rate, which is an important quantity that controls the chemistry of the ISM. And the third one is the gas phase metallicity, and we'll see new results also in this section. We'll also see how these ISM environmental parameters affect the carbon cycle, which is the C+, ionized carbon C, the atomic carbon, and CO, so carbon in the molecular form, as it is locked with the oxygen atom. And I will end up with a few words about the C+ deficits in the ISM and the C+ star formation rate relation, which is of significant importance in the extragalactic astrophysics. And the results I will show you are based on the codes, so 3D PDR, mainly the 3D PDR code, and the recently developed PDF Chem code. So to start with, what we're interested in is the actual life cycle of the ISM. And what do I mean by saying life cycle? I mean the cyclic process of star formation, the supernova explosions that we have from the star phase. We go back to the gas phase, and how the elements are populated during all these processes, and of course how we observe all the different stages of the life cycle of the ISM, from nebulae to star formation and vice versa. And we are actually interested in this particular part of the age of the cosmological evolution, which is a redshift of around 2, marking the star formation peak of the universe. This is when the age of the universe was quite young, was around 2 to 3 gigayears old, and it's of great importance to understand the galaxy evolution as a whole in terms of cosmology. The interstellar radiation field, so we are talking now about the first ISM environmental parameter. The interstellar radiation field consists of 6 different components. Mainly, it's the starlight, is the photons that are emitted from massive stars or from stars in general that interact with the interstellar medium. We have X-rays, we have galactic synchronous radiation, the cosmic microwave background radiation, and so on. And on the bottom right, you see a graph, which is the spectrum of, or the energy density of these different components versus the frequency. And if you integrate this part of the graph, you will end up with a quantity that characterizes the strength of this interstellar radiation field. And this is actually the input in PDR codes. If you are using one or if you're planning to use one, it's actually the integration of this graph. The photons are characterized as extreme ultraviolet and far ultraviolet in terms of the energy. So the extreme ultraviolet, the EUV, is when we have photons more than 13.6 electron volts in energy, which means that they ionize hydrogen. And the FUV photons, the far ultraviolet, is between 6 and 13.6 electrovolts. This is actually the interest part of the energy range that we will focus on. Now, you see on this figure here, the nebula. So the H2 region is usually marked with secular regions, and these are produced from the interaction of this EUV with the ISM. So we are talking about the ionized gas. And behind it, or around this area, in between these areas, we have the far ultraviolet photons, which are causing the photodissociation regions to exist. And this is actually where the atomic phase of the medium to molecular phase occurs. We have also cosmic rays, which the term rays is kept only for historical reasons. It's not, of course, rays in terms of electromagnetic radiation, but rather that they are charged particles, and these are actually mostly protons. Then we have some helium nuclei and nuclei heavier than helium. And because they are charged particles, they follow the magnetic field lines, so they travel in very different trajectories than photons. The other thing is that the cosmic rays, the cosmic particles, also extinguish as the FUV photons do, but they extinguish much slower. So they penetrate, they have the ability to penetrate large columns of density. And this means that they can produce some heat at high column densities and ignite also very interesting chemistry. And then we have metallicity, which is actually the amount of metals or the amount of all abundances, but except hydrogen and helium. And as we see here in this graph, the sun is located at this point, which on the x-axis we have the galactocentric radius. So as we move towards the galactic center, we see that this metallicity, the abundances of all metals increase, but when we go to the outer parts of the galaxy, they decrease. And actually, the outer parts of this galaxy is quite similar to the average conditions that we find in dwarf galaxies, which are found to be metal poor. Whereas if we go to the inner part of the galactic center, this is mostly related to more heavy, more metal-rich ISM. Apart from the gas phase metallicity and all the previous environmental parameters, we also have the interstellar dust particles, which are actually solid bodies. And you see here a real image of a dust particle taken with the Stardust space mission. The characteristic of these dust particles that they emit they produce thermal emission in infrared. And they consist of mainly a nucleus, which is usually silicon or iron or carbon, etc. And then we have a mantle. So one layer above the core, we find more complex molecules like CO2, H2O, CH2. And this is also where the H2 formation occurs. And if these dust particles interact more and more with the ISM, they produce more complex molecules, other organic molecules, and these are mostly found in protoplanetary disk areas. And of course, the interstellar dust particles, or the dust to gas ratio, so what is the amount of dust as compared to gas, changes as a function of metallicity. When we go to lower metallicity ISM, we find less and less dust. And this is also important for the penetration of FUV photons in low metallicity environments. And this is the Andromeda galaxy as seen with a Spitzer Space Telescope. And this is the emission of these interstellar dust particles in front of your eyes. So if we focus mostly on PDRs, this is the Orion bar. It's probably the most famous PDR laboratory here because of the relative angle that we have with us, the observers. And what we see here is that we have emission here from massive stars. We have the UV radiation, which goes to FUV radiation here, far ultraviolet, and then it produces a stratification of species, as we see here in this rather old but important image. We see the polycyclic aromatic hydrocarbons, then we have the warm H2, then we have CO. And what we see here is this stratification of species, which is important. But here we have a more modern or a higher resolution image showing how this transition between the ionized and the atomic and molecular phase actually occurs. And this is a recent paper by Hernandez Vera et al. In 2023. And here is they did very high resolution observations with ALMA in the Horsehead Nebula in Barnard 33, and they focused on this particular region. And what they see, what they found is that we have here the H alpha emission, which comes from the right-hand side as we see the image, from the nearby massive stars or the higher energetic photons. And then we have the transition between the ionized to atomic, which is a very thin area, and then we go to the molecular region where we have the emission of the CO transition here, the 3 to 2 transition. So do you see how very nice representation of how this transition occurs in more modern observations. Now, if we talk about the PDRs as a whole thing in galaxies, if we zoom in a particular point in a galaxy, we'll find the GMC, and around the GMC, the edge of the GMC is interacting with the photons, with FUV photons, and the edge of all of these GMCs are PDRs. But when we see a galaxy as a whole thing, most of the ISM is, we can say that it's in diffuse regions, in diffuse ISM, and in diffuse gas, and this means that most of the ISM in the galactic ISM can be considered to be in PDR. So PDRs are very important to understand the emission of different galaxies. So we're talking about a very important tool in our understanding of the galaxy evolution across the cosmic epochs. Now, if we go to break down a little bit further the PDR, what we will see here in this simple diagram, we have the FUV radiation that comes from left to right. We see here the transition from H1 to H2, so this is the atomic to molecular transition. And as the photons extinguish, also we have the transition from C+, the ionized carbon, to atomic to CO. Then we have the oxygen, and far inside at very high column densities, we have the gas phase formation of molecular oxygen. And of course, the gas temperature drops from warm to cold as the photons extinguish further and further in. So the C+ to C1 to CO, this is actually the carbon cycle that I'm talking about. And we see all of these stratification of species, which mainly depend on various different parameters, such as the age of the cloud, the starlight, the intensity of the FUV radiation, cosmic rays, metallicity, and X-rays. And in terms of observations of these PDRs, we have the line of 158 microns, which is the ionized carbon. Then we have two fine structure lines from the atomic carbon. We have various emission transitions, emission lines from the transitions of carbon monoxide. And if we put all of these transitions in a single diagram, we get the spectral line energy distribution, or the SLED. And here you see a collection of these different SLEDs from different galaxies. So each different line from these CO transitions correspond to different galaxy, which means that by knowing complete SLEDs, also in association, if possible, with different other coolants like C1 or C+ or anything else, we can disentangle the ISM environmental parameters that exist in different parts of these galaxies. And of course, we don't have here only the carbon cycle, but we have another important coolant, which is the oxygen, but we will not go through this in this work. What I would like now to focus on is the CO dark molecular gas. So as you know, we get the information that we get from molecular gas comes from the emission of CO, especially CO1 to 0. However, there is a part in the transition between the atomic and molecular gas that CO has not formed yet, or it's not emitting strongly enough in order to capture with radio telescopes. And there is a good fraction, a good amount of this gas that exists in galaxies that is molecular, but invisible to CO. And that's how we call the CO dark molecular gas. And it's actually a term that was introduced by Van Dijk in 1992. So you see here if you focus here on the column density of molecular gas here in this filamentary structure, in this particular part of the molecular structure, you see that we have the emission of C+, so we are talking about the outside part of this filamentary structure. Then we have the emission of C1, so we are actually in this middle part where we see a strong emission of C1, but then when we go to CO, in this precise part of the clouds, we see that it's not visible anymore to CO because this part is molecular but not dense enough in order to form CO. So this is a great example of what a CO dark molecular gas is. And as an alternative tracers here, we can use the atomic carbon, which was introduced by Papadopoulos in 2004, about 20 years ago. Now I will focus a little bit more on models. So the image that you saw before and also the images that I will show you later are all done with 3D PDR, in which we post-processed a part of a cloud collision simulation, which was done by Benjamin Wu in 2017. So he just took a sub-region of these molecular structures, and then we embedded in different ISM environmental parameters. So here you see that we have this is our benchmark, which is which means that we have run this model for the standard ISM conditions that we have, the solar neighborhood, if you want, condition. So the cosmic ionization rate here is the average one of the Milky Way, around 10 to the minus 16 photons per second, ionizations per second. This is the column density of H2 of molecular gas, and here you see the column density of the carbon cycle on the top, so C+, C1, and CO, and underneath you see the emission, the velocity integrated emission of the carbon cycle of all these different phases. So 158 microns, we have the C1 1,0 transition and the CO 1,0 transition here. Now, if we increase the cosmic ionization rate by 2 orders of magnitude, so we essentially take this cloud and place it in the galactic center, where the cosmic ionization rate there is higher, we see the following. First of all, the column density of molecular hydrogen, as you see, remains relatively unchanged, which means that the molecular gas survives even if we have a high cosmic ionization rate. But the column densities of C+ and C1 also, they actually significantly change. That's because CO has interacted with cosmic ray particles, and it has been destroyed through the interaction with helium+, which creates C+ and then C1. And here you see the emission of all of these 3 lines. You see that CO remains the same, or here the CO emission in the high cosmic ray ionization rate simulation increases actually, because the internal gas temperature increases at high column densities due to the interaction of these cosmic ray heating. But we see a significant impact in the emission of C+ and C1. We see that all of these 3 lines are significantly brighter than in the galactic conditions, and they are coming also from molecular gas phase. So when we have high cosmic ray ionization rates, we can use all of these 3 different lines to get information about the molecular gas content in galaxies. Now, if we do the same experiment, so we return back to the same benchmark, we use the same simulation, but now we use we increase the G0, the FUV intensity. So what we see is that the H2 is affected only in the outer parts. We have the photodissociation of molecular hydrogen, so we have a production of atomic hydrogen. We don't have significant effect here in the carbon cycle in terms of the abundances, so except for the outer parts of CO, which has been photodissociated. But we see that the emission of C+ is significantly increased, is highly increased here because of the interaction of the FUV photons that extinguish quite quickly. So you see here in relation to the slide before, that C+ here, although it's much brighter, it does not originate directly from the molecular gas as before. It stays bright, but in the outer parts of the molecular region. We have also some stronger emission of C1, but the origin of C1 and C+ and CO remains the same when we have higher FUV radiation fields. Now, I would like to go through the metallicity and pinpoint a problem that actually most of the groups actually face. So when we calculate low metallicity ISM environments, we usually we tend to linearly decrease all abundances together. For instance, if we go to a 10% metallicity, it means that we apply the same factor for the abundances of carbon, oxygen, nitrogen, and so on. But what we see from observations is actually a little different. So we have a differential decrease of the abundances of carbon, especially carbon and oxygen, which I will focus now. That is because the oxygen, if we go to stellar nucleosynthesis, to nucleosynthesis of these elements in the stellar interiors, we see that oxygen is actually produced in high mass stars and released from high mass stars through supernova type 2 explosions, which are short-lived, and as opposed to the carbon, which is of course also created in high mass stars, but mostly is found in intermediate and low mass stars, and it is released from these stars throughout the stellar evolution. The difference is that the intermediate and low mass stars are long-lived, so we have a few mega years here for the high mass stars and a few giga years here for the intermediate and low mass stars. So we have a difference between the release of carbon and oxygen, and this is actually what we see here in a figure published by Berg et al. 2019. We have here behind, we have the observations of different stars versus metallicity, and on the x-axis here we have the logarithm of the ratio of the carbon over oxygen, and we see here that we have a drop between this ratio. If carbon was decreased linearly with oxygen as we apply, then we would actually find a straight line along the x-axis. So what we see here is that we have a dip. That's because when we have the production of oxygen and release through supernova type 2, oxygen is released to the ISM much quicker, at which point, at some point, this emission halts. This production of oxygen halts, and then we have significant bursts at which we have the release of carbon. That's why all this zigzag forms, and we see that the C over O ratio goes back, has an upward trend now. So initially we have a downward trend, and then we have an upward trend, and that's because of this difference in the release of these two atoms. And this is exactly what we have done. We actually took into account this difference in the release of the abundances, and we have run models to check what are the consequences when we go to the emission of the carbon cycle. And these are the two models that we have run. First of all, both models use exactly the same dust-to-gas ratio, so this is not changed throughout the models. Then we use the same oxygen abundance, which is the standard oxygen abundance that we have in the ISM, in the solar metallicity, if you want, in the ISM of solar metallicity. But what we have done in the second model is that we decreased the carbon, and only that, by an amount that is equivalent to what we see from observations. We see from observations here at the low metallicity that the carbon is much more reduced, but we have some observations from very high redshift galaxies, for instance, the GN 11 redshift galaxy, which is one of the record holders of the longest, furthest away galaxies that we have seen. And we know that these galaxies have less carbon than we find here in the Milky Way. So that is the experiment that we have done, just 2 simulations. And of course, here, in order to see better the impact of the differences in the carbon and oxygen abundances, we use a higher cosmic ionization rates. So this is the result. On the left, you see the carbon cycle in the simulations as we use them for the solar neighborhood conditions, albeit the cosmic ionization rate is a little higher. So we have emission of C+, a strong emission of C1, and a much stronger emission of CO. If we decrease the carbon abundance, then we find some non-intuitive behavior. First of all, C+ decreases, as we expect, because we remove carbon abundance. Second is that the atomic carbon decreases, and decreases a lot, by a factor of 10, as we see in these models. But CO increases, which this is the counterintuitive part, because how is it possible that when you decrease the abundance of carbon, you increase its emission? And this is because by removing carbon abundance, it means that we remove a coolant. Therefore, the entire gas temperature will be a little warmer than with carbon. And the second is that because we have less carbon overall in the ISM, it means that we can see much deeper in the clouds, that the leftover of carbon monoxide will immediately come from the very dense regions, which are also quite bright. That's why we see this brightening of CO. So the prediction here is that we will have a condition where the galaxy or the cloud will be CO bright but C1 dark. And actually, this is what we have seen recently in paper published by the group by Michiyama in 2020. So this is the NGC 6052. It's a nearby galaxy that is actually a merging system. So we have 2 galaxies that merge, and we observe them during this merging process. And the star formation rate is elevated, is around 20 solar masses per year. And the interesting part is the red contoured region here, where it is bright in CO 4 to 3, but dim in or dark in C1 emission. You see here with ALMA observations that we have a galaxy that is CO bright, but C1 dark. And this is actually one of the first galaxies that we have seen that have been characterized as C1 dark. We have, at least to our knowledge, another 2 examples, but we believe that sooner or later we will have more and more galaxies that come up as C1 dark galaxies. And one of the theories that we propose is that in systems like this, we expect to have an alpha enhancement, which means that we have a higher abundance of oxygen due to the higher amount of supernovae explosions or massive stars, which leads to type 2 supernovae, which means that we will have an enhancement in oxygen. And that's our explanation of the C1 dark galaxies, that we have a higher abundance of oxygen there. And finally, I would like to talk a little bit about the C+ deficit, which is a problem that we, an open question, an open problem that we have in extragalactic astrophysics, or actually in astrophysics in general. And by C+ deficit, what I mean is that the ratio of C+ over FIR, which is the emission of C+ divided by the emission of dust, decreases as the FIR emission increases. So in few words, you have a galaxy which is bright in dust, which means that you expect to have a high amount of FUV radiation or a high amount of ISM environmental parameters. But when you observe it in C+, you see that you don't observe the C+ that you expect to see. You observe less C+ emission than you expect to see. This is a question why observe this. And there are various models that have been proposed, but what I will show you is our approach, which is the thermal saturation. And this was done with a model. We used a dwarf galaxy collision model from the Griffin project initiated by Natalia Lahen in 2020. And the characteristic of this simulation is that we have a star formation rate that spans more than 2 orders of magnitude in a single simulation, which gives a wealth of data to understand how the C+ emission and the FIR emission actually evolves. These are different snapshots. On the top, you see the column density of this collision, this merging of the two galaxies. You see that we have cluster formation, massive star cluster formation. So each cross corresponds to a collection of massive stars. The second panel here shows, the second row shows the C+ emission, and the bottom one shows the FIR emission. So if we focus on one particular time at 170 megayears, where we observe 3 different clusters that have been formed, and we focus on cluster 3, which is the most massive one, and on sitting also on a quite dense region, then you will see this. So the C+ emission here is on the left panel. The middle one is the FIR. And if we divide those two maps, so we will go to the C+ over FIR, then we will see that in the place where the massive star cluster sits, we get a low ratio of C+ over FIR. So in this part, the C+ is deficit. So we have a C+ deficit ISM. And underneath, you see observations from the trapezium, where we have the C+ emission on the left. In the middle, we have the FIR emission, where the massive stars actually are located. You see that in both cases, we have a bright emission. But when you go and you divide the two maps and you want to see the C+ over FIR, you see that in the place where we have these massive stars, the ratio actually drops, which is an excellent agreement with our models. And it drops because we have a production of photons there. And what photons do, as we can see here in the series of PDR models, is the following. So we have here 6 different PDR models where we use where we vary the FUV intensity from G0 of 1 up to 1 million, up to 10 to the 5 or more. And you see already here that the C+ emissivity actually saturates. We have the thermal saturation of the C+ emissivity. So the emission of C+ cannot go higher even when we go to very high G0, up to 1 million. Whereas the emission of the FIR, of the dust emission, actually scales almost linearly with G0. So if you divide the two graphs, or if you divide the amount of C+ emission divided by the FIR emission, then you will get this drop of the ratio, which means that as we increase the FUV intensity, we have a much lower ratio of the C+ over FIR. So you are C+ deficit. So our explanation is that C+ deficit may occur from strong FUV intensities that we can have in different systems. And one last slide is that C+ can be used as a star formation rate tracer. This is known a few years now from observations. So you see here different parts of observations, or either individual observations or a collection and best fits results. And the colored dots correspond to our models that I already showed, the dwarf galaxy merging. And what we see is that we have a very good agreement with the star formation rates and C+ relation. And also we confirm again that C+ can be used as a star formation rate tracer in extragalactic observations. And here I will leave you with my conclusions. So actually the conclusions, the take-home messages I would say is that cosmic rays can severely destroy CO, but not H2, as we saw in the first part of simulations. When you go to FUV intensities, this can explain the C+ deficit gas, as we saw now in the last slides. When we go to metallicities, we find that the C over O abundance ratio is a very, very important parameter. It's a much more important parameter than we initially thought. And it's actually as important as cosmic rays and FUV intensities are. So we can say that it's an independent ISM environmental parameter that we have to seriously take into account, because the C over O ratio can change the chemistry and the line emissivity, and it can potentially explain C1 dark galaxies that we now have some first observations published. And of course, C+ can trace the star formation rate, as I already explained. So thank you very much, and I'm open for questions.